what's new in nCode 2022. So let's get started with GlyphWorks and VibeSys first, right? So in GlyphWorks 2022, we have a new glyph, which was actually out in the media release 2021.1, but in this version, it's got more capabilities, right? So this electric power glyph, the good news is it's part of the fundamental palette, right? Basic DSP. So there's no extra cost involved or what. Just all you need is to update your version of nCode, and you'll get access to it. And it calculates electric power, mechanical power from measured parameters. Obviously, for the electric power, you need current and tension signals, whether we're talking those signals coming from the battery or in the output of the inverter, for instance, in an electric drivetrain. So it will calculate the electric DC power, AC power, mechanical power, and therefore it can estimate the efficiency of the inverter, efficiency of the electric motor, efficiency of the whole drivetrain. And the nice thing is you can display that in various fashions. So first you can display the power signals that it calculates in a time series, but you can also display typically the efficiency in an efficiency map. So you'd have the shaft speed in the x-axis, the shaft torque, and on the y-axis, and the z-axis top view showing basically the efficiency, or it could be the power or any other parameter. So we have this nice efficiency map that's available thanks to the surface plot glyph, which is also a fairly new glyph, right? So in your displays area, you will find a new display glyph called the surface plot. And all you need to do is connect it to some signals, for instance, and in its properties, it asks you which signal do you want to adopt for the x-axis, which one do you want to adopt for the y-axis, and which one for the z. And you get those fantastic top view colorful plots, right? So in order to help you use the electric power glyph and the surface plot that could be associated with it, we have a new worked example. And in order for you to understand the math and anything you need to know more technical depths, we have a technical background in the help. So please take a look, enjoy, let us know of any question. And now if you take a deeper look at the electric power, especially the AC electric power that this glyph calculates, in its first basic version in the media release, it could calculate the time averaged power. So over a given amount of time, it averages the power, multiplies tension by current and takes an average power. So that's one of the options that you can pick and choose from, and this will produce typically the power that are such as typically is calculated today with in the power analyzers on the market, right? So that's the classical standard approach to calculating power. Now, what we added in the version 2022 is a new and unique additional method called the instantaneous method. This one offers far more accuracy, especially for reactive apparent power, and also, as its name indicates, a much higher time resolution. So you could look at the power signal through a microscope, if you will. So in red here, for instance, we have the reactive power with some peaks of reactive power. And just below what I've plotted here are the three-phase tension signals, for instance, coming out of the inverter. And I'm zooming here, and you can really zoom down to the single digital points, right? And see how the power evolves in time in relationship with the waveform of the tension, for instance, right? It's using pulse width modulation, and you, as a user of an inverter, you may have some tuning capabilities. You have knobs. You can change the way the algorithm works, produce different waveforms, and therefore using this you can understand really the impact of the parameters you set in your inverter. the impacts that can occur in the reactive and apparent power in output, right? So this is one of the main highlights in this release for GlyphWorks. It's the electric power glyph, and basically it's targeting electrification engineers because they can optimize the electric powertrain, and therefore increase the vehicle range. So for a given battery size, you want to make the most, optimal use of it and turn the electric power into mechanical power at the highest efficiency possible, and therefore you increase the range of your vehicle, right? So this is about the electric power, and I'm going to show you. I'm going to do a quick demo after in a few minutes of this glyph. In terms of displaying data, we developed a new feature in the XY display where you can automatically see X cursors positioned on the highest peaks of the data. So as a user, you can define how many cursors you want. By default, it's 3 cursors. And those would appear on time series data or on histograms, like 2D histograms or frequency spectra, for instance. You could use this feature on all those sorts of data. It could be adaptable to the zoomed region. So if I was zooming in the middle of this section here where you see no cursors, right? It would recalculate the 3 maximum peaks and position 3 cursors, right? That's this option, that checkbox here. So it makes it very easy and handy to use and give you very quickly the information you're after, which is, when did my maximum peaks occur? So you can choose just 1 peak or 10. It's a user-defined thing. And the nice thing is you can save it as a default configuration. So anytime you look at a signal or at a spectrum, you get those cursors displayed on top. Now, those cursors can be customized. Their appearance can change. All user-definable appearance. So you can change the color. In this example, I've picked blue cursors, their thicknesses, the style, and level of transparency, and all this appears. In the toolbar, you've got this button there that defines basically the cursors, and that's where you'll find those properties to turn on or off the peak cursors that I just introduced, and also change their appearance, right? So that's a very handy, very, I believe, a useful thing that we have in nCode 2022. And basically, it improves the readability of the results. Now, still, in terms of displays, I think we've introduced that in the media release, but it's so appreciated. I think it's worth repeating it. So we enhanced all of the displays basically, like the histogram display, waterfall display, X, Y, Z display, with additional colors and relative color palettes, right? So instead of going from the classical red to blue, you can pick and choose other palettes. Like here in the surface plot, I decided to go with the blue-yellow palette, right? You see, and this histogram, I believe it's the blue scale palette, right? This waterfall here is using the black, magenta, white palette, etc. Right? So it offers, especially if you get a report with multiple plots, and you can have a variety of colors, making it nicer, maybe more modern and easier to read, and sometimes one palette or another would pinpoint some singularity or something. So overall, I believe it improves the readability of the results again. Right. In terms of updates in the software, as you know, we make extensive use of Python, and you can create your own glyphs using the scripting glyph and use of Python or MATLAB. So now we're supporting Python 3.8, and you can also use Python 3.6. Right, so it's a preference. By default, it's 3.8, but you can change that to 3.6. And by the way, Python 2.7, which we used to support or to accept until recently, it's now entirely dropped. So if you still have some Python routines in 2.7 and want to update to nCode 2022, please think of upgrading those Python routines from 2.7 to 3.6 or ideally 3.8. Contact us if you need some help. We can probably help you with that. Anaconda, which is a Python distribution, Anaconda 3.6 is now officially supported as well. So with Anaconda, you get all sorts of libraries that come along, like NumPy, SciPy, and all sorts of data science or machine learning, etc., and libraries. What else? We support Microsoft Office 365 now. So that's for the Excel input glyph if you want to read XLS files, or for the Studio if you want to create Studio Glyph if you want to create some reports automatically. You can export them in Word or PowerPoint, and we support Office 365. MATLAB, as I said, we can use the scripting glyph with either Python or MATLAB. We support MATLAB 2021b now in the scripting glyph. And last but not least, the file formats. So we are the latest version of the DXD file format from dwsoft. Similarly, we upgraded a number of other file formats like the TDMS from National Instruments, or the BKC and PTI formats from BKS, well, formerly known as BKSV, now HBK, and also the vector MDF format. So now we support up to MDF 4.2 with the latest update, basically. So we make sure that, at every version we are up to date with the latest third-party components. I think that's it for the GlyphWorks part of things. Let me just now do a very quick demo. Let me just share nCode here, and we'll go through a very basic demo. So here, I'm going to show you the electric power glyph together with the surface plot here. So I've got in input, I've got a very large time series, which actually is the concatenation of I think it's like 35 snapshots, each lasting like a minute or two at a very high sample rate. And in there, what is it we have? In each of those, we have the three-phase current, the three-phase voltage, the continuous current and voltage out of the battery, and the speed and torque of the shaft of the motor, right? So, and we've done snapshots at various speeds and torque on a test bed, right? So I've got all those measurements in there, and I drag them all into this CS input glyph, and let me press play now. So I'm doing a bit of filtering up front to remove the high frequency harmonics maybe, or some high frequency noise, and then I'm using the electric power to obtain the waveform, the time series waveform, right, of AC apparent power, AC reactive power, also the power factor, the DC electric power, and if you move to the next channels, you'll see the mechanical power, shaft torque, rotational speed, etc., right? And the efficiency, DC to AC efficiency. So that's, in other words, that's the efficiency of the inverter. And we can display that in a surface plot. So very easy to configure. You double click and you assign some channels to the various axes. And here we see the efficiency in percent, AC to mechanical efficiency. So that's the efficiency of the motor, right? And we see at which speed and which torque the motor is more or less efficient. And now, so this glyph, if I double click on it, it asks me what you want in output. So you can ask for all the AC, DC, and mechanical power, the power factor, and the efficiency. And under advanced, that's where you use, you define some of the properties, the calculation properties, but mostly it's about mapping the channels, right? What are the channels corresponding to the current, the AC currents, and etc., right? What is the speed channel? So you enter here, the usual way, if you're familiar with GlyphWorks, either numbers, or you can pick a channel, or you can use metadata, etc. Note that we have this averaging frequency here. So we're producing the output signals at 10 hertz, 10 points per second. So it's averaging, every tenth of a second, it does an average of the, to calculate the power in this circumstances, right? So that's the first very basic demo that I wanted to do. Another one is illustrating now the power signal microscope. Now I'm no longer using the method that I used in the previous example. I changed my method from time averaged to instantaneous. And also the averaging frequency is no longer 10. It's now 500,000 hertz, right? 500,000. So we really producing power at a very, very high rate, right? And we're using this new instantaneous method. Let's check out what we obtain in output. Let me run this one. It might take a second or two because again the input data is quite huge. So here I'm displaying the reactive electric power together with the three-phase voltage signals, right? And if you zoom in, you will see the pseudo sine wave corresponding to the three-phase voltage. And as you zoom in, you go more and more into details. By the way, the voltage signals are sampled at 500,000 hertz as well. So 0.5 megahertz in this case. And you can really relate the waveform of the reactive electric power to the waveform of the voltage signals here, right? So you can really see that we're using pulse width modulation here, the typical waveforms of it, and what is creating maybe a peak in the reactive power. We'll do a dedicated webinar on that soon. Stay tuned, or check out our website. But in the next 2 or 3 months, we'll do a webinar on that with a nice example showing the use of it. Let me end my demo with a quick use of the max cursors. So let me display, well, right, forget about that. Yeah. So here I've got 3 channels. If I click on this button here in the toolbar, this button here in the toolbar, right, that's where you can set up a number of things to do with cursors. That's where you will see the peak X cursors. By default, it's unknown, but I can ask it for the local to be showing the local max, and I can ask for the 3 or 4 to 5 maximum peaks cursors, right? And this checkbox is checked, so it'll show the cursors in an adaptive fashion. So as I'm zooming in, it will adapt and show the cursors in this zoomed area. So let me show you how it works. So if I go OK, right? Let's take the green signal here. It's showing me the 3 cursors corresponding to the 3 peaks there, right? Now let's zoom in the middle section here, and it's adapted, and now it's showing me the cursors corresponding, the max peaks, corresponding to this zoomed area, right? Etc. etc. Sometimes they're very, very similar, very close. Sorry, if your signal is very peaky, very noisy. Sorry, etc. etc. Right? And this can be done on time series, as I said, or can be done on PSDs as well using the viewer, right? You've got the available data window on top. You've got the little viewer button, so you can decide to look at data this way, and you can ask for. Let me separate those and ask for again the 3 max peaks. So you see at which frequencies you've got the maximum peaks in your spectra in this example, for instance. So that's an example use. And again, you can save this as a config file so that next time you look at a spectrum, you will see those cursors automatically being on your graphs. I think that's it for me in terms of demo. Now I'll pass on the ball to to Paul. And please, if you have any questions, put them in the chat, and we'll cover them later. Thank you very much.
Fred. Okay, so thanks for that, Fred. Now I'm going to cover what's new in DesignLife in 2022. So the first thing to mention is we have added another possibility for entering material definition. So for a typical DesignLife job, we will need definition of the stresses, the loads into the structure, and then also the material that's used for the different parts of the structure. So we've added the ability to read those material properties directly on a per entity basis from a formatted CSV file. So this allows a different property in the model for every entity you're analyzing, either every node or element you're analyzing. So this is particularly useful for if you've got some sort of software that's generating material information. For example, if you're doing a casting analysis and you've now got a different material property for each entity, you can export that directly, and we can pull that in to do an analysis based on a particular material definition for each part of the model. And that's available for standard SN, standard EN, and also multi-temperature EN analysis methods. So this also includes default properties. So you can use this to set one material for the entire model by setting, see the section there at the top of the header where you can set all the material definition at the top. So you could use this just to set one material for the model, or for every entity in the model, or a mixture of both. So if you've got some entities where you've got specific material data, you can define that and then default the rest of them to the default sections. So it gives you a lot of scope and flexibility for where you want to define the model, and particularly useful for non-homogeneous materials such as castings, even additive manufactured components where you've got specific information on the material properties in different parts of the model. So it gives you much increased flexibility in the application of material properties. Second thing we've added, we have a multiaxial EN analysis method, and that's used for when you've got multi-axial loading into the structure. So we've already got the Wang-Brown solver in there, which is very high resolution, very good method for non-proportional loads. We've added the Brown-Miller option. So Brown-Miller is for predicting fatigue damage and general multi-axial loading, but doesn't capture things like ratcheting or additional hardening that occur from non-proportional loading. So it's not as accurate and not as applicable to all stress states as Wang-Brown is, but it's significantly quicker. Wang-Brown's doing a lot more complicated calculation, so it is quicker. And if you've got proportional loading, will give you a good result. There's also extra theory in the documentation to show you exactly what that's doing. So this was a customer request from a couple of different customers. So it's a continued help to the customers to respond to their needs by adding extra options. The next thing we've added is we have a Hotspot Glyph that will identify geographically separate areas of maximum damage or minimum life or safety factor. So that's already in the software. We've added the ability to include adjacent locations to that. So the hotspot will generally give you a number of hotspot locations or a number of hotspot locations per property set of the material, for example. So you could ask for 5 hotspots on each particular part of the model. But now you can turn on adjacent locations. You'll get the results for the adjacent nodes or elements next to that hotspot. So this gives you the ability to examine variation of the results around those hotspots. So particularly if you've got one high stressed area, you want to know whether that stress spreads out from that point or whether you've got a singularity at that point. Also, it gives you a good idea of the variation from that point of the damage. So it's a good way to look at the fidelity of the model, to be able to tell whether you've got good results or whether you've just got some odd singularities in the model. That's just added another tool to investigate FE model fidelity amongst all the others that are also there in DesignLife. It is also implemented in the elimination post-processor. So during the analysis, if you've got multiple runs where you're doing a quick analysis on all the model and then doing a second run on a smaller part of that model and doing a more complicated analysis, you can now either just select the hotspots for that final calculation or also the adjacent elements or nodes. The next thing we've added is some functionality to the virtual sensor within DesignLife. Virtual sensor was added a few versions ago. For a long while, we've had a virtual strain gauge, so you could put a strain gauge on your FE model to correlate with test-based measurements, for example. So you could look at stresses and exactly where you've got your strain gauge and pull off the triax stresses, for example. We then added a virtual sensor, which was initially to do displacement results. We then added velocity and acceleration, and since then force as well. So from a time-based analysis, you could extract your forces at a spot weld, for example, or extract your accelerations to look at accelerations in the model if you got the correct time-based analysis. But in this release, we've added the ability to take displacements based on a vibration analysis from your FE. And also enable then the PSD output from that. And in terms of output, you can select either displacement, velocity, or acceleration output. So in effect, you can add what is primarily a virtual accelerometer to your model. So this can then generate data for correlation purposes, for example. So if you've got test data for measured accelerations, you can correlate directly with the model. You can also use that acceleration, for example, to extract local accelerations on a particular part of that model, which could then be used to drive a separate FE model or to generate a test specification for that component based on the assembly FE. I'll just show you a quick demonstration of that. So this shows a very simple FE model. In this case, I've got one sensor on there already. I can simply add a second one. So if I add I can tell whether I want to look at the surface normal for that model. So if I look at the tensor from surface normal, pick we'll go for node. I can decide the orientation of that, apply that. So now I've got new sensor with a particular coordinate system to line up exactly with what you've got in terms of your test. And I've got 3 examples of the glyph here where I can select. In the first example, I'm selecting displacement in terms of my output, and the other 2 are set to velocity and acceleration. So very simple. This is a modal-driven job. So in the FE, I've got modal results for displacement. I've got the modal coordinate inputs to create the frequency response function internally, and then I've got a vibration generator for generating the input PSD. So for that global PSD applied to the entire structure, I can then extract displacements, velocities or accelerations in terms of the different coordinate X, Y, Z, and then for the new sensor I've just added again for X, Y, Z from that. So it gives you a very good tool for correlating between test and CAE, looking at the validity of your models, and then generating test data that then can be used for particular parts of that assembly. So it makes local PSD's acceleration much easier to generate. It's possible within your FE package to do this, but it's much more complicated. You have to set a lot more things up. And once you've done the frequency response function, you can then do this for any part of the model you like. Next thing, we've updated quite a few of the materials in the standard database. We've added constant and variable amplitude versions of all the original seam weld datasets. The datasets that are in there currently are for variable amplitude loading. We've added the constant amplitude variants, left the original named ones in, and also added the variable amplitude, so it defines exactly what you're using. We've also Added 2 new aluminium seam weld data sets, which there wasn't any aluminium seam weld data in there to begin with, and also a new ASME steel seam weld data set from the ASME standard. And we've also added 4 new materials to the premium material database that is available via the token system. It's continuing to provide world-class materials data. So if you have any requests for material data you would like to see in the premium material database, just let me know. It's always useful to know what the customers want in terms of materials data, and we'll always look at seeing whether there's a general reason for adding that material. And some other smaller developments that have gone into the release. We are able to generate FE input tables for time series data to be applied to ANSYS, Abacus, and Nastran, for example. So from your measured loads, as Fred showed you, you can then take those and generate FE tables. We've now had the ability to name those tables for Abacus input files, so it's a bit easier to then recognize within the FE tool where they've come from and what they are. We've added support for PAMCrash FemZip files. This is a zipped format file that we've supported in terms of Nastran for a while. We've now added the PAMCrash version. So this allows you to use these files directly without unzipping them externally. We were asked to add the ability to read modal coordinate input files from LSDyna. And in conversation with the LSDyna developers, they have then decided to actually support the standard ANSYS MCF file format, which means we can now read them directly from the latest version of LSDyna. The load reconstruction GlyphWorks, which is one of the ones that takes input from virtual strain gauge, we've now just added some more detailed metadata and then the ability to set the channel titles for the output load histories that are generated. And in terms of spot weld, there are lots of statistics you can output for a spot weld analysis. We've added one extra one, which is the actual sheet thickness for both sheets that contribute towards the particular spot weld. These sheet thicknesses are used internally to calculate the spot weld diameter, which we also output, but this gives you the ability to look now directly at the sheet thickness and gives you some idea as to what might be the issue. For example, whether you've got one very thin sheet with a very thick one. Gives you the ability to drill down a little bit more to work out where any issues may be coming from. And as usual, we have updated all the standard file formats to support, where we support all the major FE codes, and increased our testing coverage to cover all those new versions. So another way where we continue to respond to customer requests.